Today we're going to discuss the paper 2017 Squeeze and Excitation Network. It is a work from Jin Hu, Li Shen, Samuel Albany, Gang Sun, and Enhua Wu. In these presentations, I will try to show you the high level of the intention for squeeze and excitations, and we're going to talk about how you implement it and also the overall performance and computational overhead. So let's jump to the next slide. The inspiration for to come up with this idea, this new architectures of squeeze and excitation block, it is because in traditional convolutional operations, right, it's always both spatial and also channel-wise informations. If you think about the convolution process itself, it's actually go through all the spatial information, and at the same time, right, this convolution is penetrate through the whole net channel-wise. So there is some embedded informations already combined from both spatial and channel-wise information. And a lot of papers already focus on the spatial way of how to do a different spatial combinations to make sure they can enhance the performance. And this paper will focus more on the channel relationship for the convolution architecture. So we're gonna talk about first again back to the original convolutional neural network, and we think about how can we reinforcement the feature representation, because that's essentially what we want to do, right? What we want to do is to make sure our convolutional neural network can really learn the features from the task we want to perform. So if you think about the enhanced representations, the convolutional neural network is a bunch of different operations from the convolutional layers, from the max pool, that will be a downsampling, and also there's activation functions to produce in the whole set, this whole set of operations to produce a representation of a certain image, right? And as I already mentioned, the previous research, they focus more on capture the spatial correlations between features, but there is not much research focused on the channel-wise informations. So in this paper, uh, the squeeze and excitation, they will focus more on the channel-wise information, the correlation between them. So the proposal, I will jump right into the final result, and then I will bring back to the detail later. So the final proposal, right, for this paper is the squeeze and excitation block. And you can see the diagram there. So you have input like a feature map, or you can say it's an input image. It depends on which layer you look at into it. And then you with a bunch of transform functions, right? That could be convolutions, and that will produce a U as another feature map. And of course, after a convolution operation, you will have a different width and height and also channel information. And then in this paper, instead of continue another transformation, we will bypass a squeeze operation and then an excitation operation. We will talk about later what is the detail of that. So in this paper, it just proposed this two block. That's why we call squeeze and excitation block. Okay, this is it's a series of operation contains two operations. Okay, so it allowed the network to emphasize the information features, and then also allow to suppress the less useful information. Because after you see this final output, I really like these pictures that it really tells you the channel-wise information is being recalibrated. So we already from the before, you don't have any special information of the channel-wise information, and after the excitation operation, you see the different color encoding, and that means the different weight of the channel. So some channels, I don't there is no which channel is more important here for the color encoding, but we can assume The red color means the more important channels, and the light red here is the less important. So this is just give you intuitions after these two um, operation, which is we call SE block, squeeze and excitation block, then your feature map will be um, focus will be attentions based on their channel information. And that is exactly what this paper trying to produce. So we're gonna see a little bit more about motivation, and here contains a bunch of math. And let me try to explain. This is quite intuitive. You can pause here and to read this text here. But what really the motivation behind this operation is really when you think about a convolution operation right here, transformation function here is just a convolutional operation. And how you do convolutional operation is basically you have this kernel, like 3 times 3 kernel, and then you will scan through all the feature map here. And at the same time, right, you really penetrate all the channels because this 3 by 3 and will times C command here. So you will go through all these channels and then you produce a next one point here, right? And then you have a C in total C numbers of filters. So you will generate those results. So when you do the convolution operation here, actually you imply the information of the channel already during your original convolution operation. So that is why it is also very important to know what is actually the channel-wise information, the depth information you consider here. So that's why the author argued that you can use a series of operation, which is SE block here, to find out which channel is more important, to find out the importance of the channels. Because you already imply that in your convolution operation, they try to make it focus by this SE block. And that basically is the text what it's trying to provide here. You can read by yourself. So really it contains with two operations, and that is a squeeze and excitation. And what squeeze do is actually just literally means squeeze it. So it just gives you a feature map over a global average pool to squeeze in the spatial wise down to 1 times 1 times C. So you can think this height and width get squeezed into 1. So all this here gets squeezed into 1 and produce only remain the C channel here. And that's as simple as that, just a global average pool. And excitations, it's more sophisticated. Later we will talk about that. So in excitation, basically it contains fully connected layers and a bunch of different operations to make sure you have this attention model here. So this is a high level view. In a squeeze, you have a global average pool. In the excitation, you have a fully connected layer. And what the math here, right? Global average pool is quite easy, quite intuition. And actually the physics meaning behind that is that just a global information embedding, right? Because you have those informations originally spread out on your specialized H and W, and then you squeeze them by the average. So that's think about this 1D here, this 1D channel, and then 2D on the spatial information. You basically take that information, right, and you average them, and you generate only one output here. So you take the importance of the informations and you just average them here. And what actually you're doing is you just compute the average across this 2D surface, right? And then you have a final output. And very important thing is the author put it here. They choose a simplest aggregation. Just aggregation here means you just add everything together and then divide it by the 2D surface, and that is the average number. But you can actually do more sophisticated strategies. You can do like max, or you can do like average here. It depends on what you're trying to do here. And this actually gives space, a chance for the future papers. Some papers they argue, the more latest, the recent paper they argue that this is, you shouldn't use average, you can use max as well. Probably in the future we'll talk about that, but now at the moment we just think about this is the easiest thing we can do to condense this information into just 1D, right? I'm just talking about this 2D information we just condense into a 1D information, but when you cross channel, then that would be a 1 times 1 times C. And that is actually what it do is global information embedding, try to condense the information into one point. And for the excitation part is more sophisticated. So when you let's first look at the here, right? We have this 1 times 1 times C, which is the output from the previous squeeze operation. And then we go over this excitation um, operation, and that become this activated versions, which one should be more in attends, should be more in focus. So what it actually do is you can see the text here. You can also pause and read that, but let's try to look together. Um, this operation, excitation operation, basically contains um, few things. The first Z, the Z is the input you have here, and the weight W1 is actually because it contains two fully connected layers. So this is the weight. And then after the fully connected layer, you have a ReLU, which is activation function. And then you pass, this is just a simple, the most simplest convolution operation, right? You have one weight, and then you have the activation functions, and you times another weight, and then you have a sigmoid functions here. Also another activation function, but just different. This is ReLU, this is sigmoid function. But the magic here is actually the dimension. If you see that W1 is that it's not original C because our input Z is original C, and then R W1, sorry, it's a C divided by R. And what it actually do, I try to sketch here, is the original Z is here, and then I vertical into this look like this, right? And its dimension is C here. It's a length of C, and then you pass a W1, which is exactly here, and that is the weight, right? So you connect with a fully connected layer number 1 here, and you have another fully connected layer number 2 here. And the important thing is there is a compression ratio R here. So what you do here is simply a bottleneck connections. You have a, a larger dimension, you compress into a smaller dimension, and you make it back. So from outside, right? From outside, when you see here, nothing changed. The dimension is still the same. But you know that inside this excitation operation actually contains two connected, two fully connected layers, and then there's a compression between there. So here is actually the magic to do this channel-wise dependency. You find out because those weights, right? You can learn that. This is exactly what we're trying to do during the training. We're trying to learn the weight representation, and those weights are actually telling you the dependencies of the different channel. Because remember, this is across the channel information. So we know that this channel may be more important than that channel, and that is exactly the output for that. So we provide another degree of freedom to let um, our network can learn what which channels is more important and what is their dependency of that. And that is actually the most valuable information that this paper trying to provide. And of course, if you have this, you have additional computation, right? Because you have more parameters and you need to do another two fully connected layers, and later we will talk about the performance overhead. So now you actually can understand the beginning when I show this diagram. You have a squeeze operation, which is doing a global average pool. And here, excitation, you do a two fully connected layers and try to make sure so you understand the dependency of the channel-wise information. So this is just a one SE block applied in the arbitrary layers. And actually, you can put this architecture everywhere across your backbone, right? So it's a generic building block. So we all know that a convolution, what it's doing is in the early layers, you can find out like a rich feature information, and those features is a class agnostic manner. Means it doesn't matter when you change the class, because in the early layers you have this age, this corner informations, and that is independent with the class. And in the later layers, it can excite the information of the class specific information, because we know in the later layers on the convolution, it is more semantic information and you contain more rich information specifically to the class. So you can apply the SE block across your network, and depending on your personal choice and depending on your trade-off of the computation as well. So the good thing of the SE block is it can be directly applied to existing architectures. And what does it mean is when you think about this is a previous diagram, I just make it 90-degree, and when that's plugged in to the inception network, right? It's just here. What it do just squeeze global average pooling, and then excitation, you already know, two fully connected layer. In between there is a ReLU, and you all know that there is a dimension compression from the C compressed to C divided by R, and then back to C again. So the dimension remain. That's why you can bypass them together. And if in the famous ResNet information, and it just you still plug this thing in and with the residual block, and then you just do a normal thing exactly like what you did in ResNet. So this SE block can really apply anywhere in your network. Okay, so we're going to talk about a little bit of the computational overhead. So when you think about back to the squeeze, right? Squeeze, what it is just a global average pool. So there is no extra parameter. It's just a averaging um, the information in the block, right? So this is a minor thing. And the excitation is more problematic. Let's say like this, because it's a fully connected layer. We know that fully connected layers always introduce a lot of parameters. But the thing is, it depends on where you apply your excitation block. So in reality, in the papers, it said in the because we know that in the later convolutional stage, right? If you think about here, the ResNet, you know that the channel-wise information will keep increasing in the later layers. So you can actually apply the SE block in the earlier layer instead of the later layers. So you will have less channel information. That means you introduce a little bit less parameter here. This is just a practical trick here. But from the high level, it introduce extra parameters, which is this W1 and W2, which we need to learn it, and that is the additional computational overhead here. But in general, these two operations produce a really minor computation overhead, but it increase the performance, so it's worth to do it. And we can see the final slides I have here is the performance. And we see that, and let's see this re-implementation part, and then the squeeze and excitation part. So it take the resonant 50 and it re-implemented it. The author re-implemented it. So the G-flops is 3.86. And when you put the squeeze and excitation, it just increases a little bit. You see, it's really minor. And then you see the performance increase. And that is really the value, right? You have a little bit overhead on your computation, but to do in return, you got a better performance. And that is the values of the uh, squeeze and excitation. So let's try to recap back to this proposal. This paper is trying to provide a generic block what you can implement in the existing architecture, which contains two operations. One is squeeze and the second is excitation. In the squeeze, in this paper do is just global average pooling. And in the excitation, it is adding the two fully connected layer and then try to have a dimension reduction in between and then return back to the same dimension so you can add them together. And that costs a little bit overhead of your computation, but in return you have a better performance. And that is for this paper. Thank you.